So, good morning, guys. So, continuing our discussion. So, after we knew how to the last topic, how to categorize polarity in terms of symmetry and in terms of polarity, in terms of bonds and symmetry, we come to identifying intermolecular force. So, first, may I write the intermolecular force or intermolecular? Some books call it bonds. So, there are actually four. In this book, you just follow this book that we're following. One is the simplest of them is dispersion forces. Um, dispersion forces. May I just list first all of them? The second one is a dipole-dipole force. Dipole-dipole force. Dipole-dipole force. The third one is in ion-induced. Ion-induced dipole. And the fourth one is a dipole induced dipole. And the last one is a hydrogen bonding. So there are five. Okay? So those are the five. First, actually, you can imagine them in terms of polarity. In terms of what substance polar, ionic, and nonpolar. For both nonpolar molecule, a nonpolar molecule near a nonpolar molecule, let's say you have CH4. Of course, if you have a tank of CH4 or a tank of LPG, which is a CH38 and a C4H10, this one is a nonpolar substance, and another one, this one also is a nonpolar substance. Of course, there's a lot of them in LPG, in terms of molecule. So the only force between them, if they are nonpolar, with respect to a nonpolar molecule with a molecule, intermolecular. That's why we call them intermolecular, because a molecule versus a molecule, what is the force in between them? Maybe we can draw it as somewhat dots here, because these are only interaction, or you can just think of it as electromagnetic waves or signals or anything that may somehow have interaction. So this force, we call it a dispersion force. Actually, every molecule has dispersion forces as long as it is near with another molecule, whether it is not a nonpolar substance, it's a polar. But for nonpolar substances, it is the only force that is in between. Okay, so that's why we discussed it first. So for nonpolar molecule, nonpolar versus nonpolar, a nonpolar near a nonpolar molecule, the only force in between them is a dispersion force. But of course, all other molecule has dispersion forces. For example, this second one, dipole-dipole, if you have a polar substance with polar substance. So the only difference here is because those polar to polar, actually dipole-dipole force, which is stronger than the usual, is categorized in the number 5, hydrogen forces, which has its own characteristic. Okay? So as it is not hydrogen forces, and you have two non-polar substance, I mean polar substances, water has hydrogen forces, so water is not really a dipole-dipole force. But generally, you can call it a dipole-dipole force, but it is a stronger, and it is categorized as hydrogen force. You can read it in the book, actually. But that's what I'm just saying, that if it's polar versus polar, look at it if it does not categorize as hydrogen force. If it is not, then it's a dipole-dipole force. Okay? So a polar with a polar molecule. So both are polar. While an ion-induced dipole, you have an ion. You have an ion near a molecule. As long as you have ion, because the highest charge that you can get are ions, which really has, I mean, the other side of the story with respect to covalent and non-covalent, of course, those non-covalent, which are ionic substances, are on the opposite realm. So if you talk about charges and you have ions with respect to other types of molecules, so that force in between them is an ion-induced dipole from the name alone. So ion wins. So ion-induced dipole. Okay? As long as you have ions, let's say you have sodium near water, you have sodium near acetic acids, that is CH3, COOH, or C2H5, maybe acetic acid C2H5, I'm not that sure. Maybe, but this particular compound, as long as it's near the ion, or you have potassium, you have magnesium, okay, all those ions and minerals, you can imagine those ionic substances which are um, dispersed through its positive and negative charge. You have an OH, okay? You have an ion with respect to a molecule, near a molecule, any kind of molecule, or whether it be polar or a non-polar molecule. So that force would be an ion-induced dipole. From the name alone, ion-induced dipole. If it is a if it is a dipole, if it is a polar versus, I mean, near a non-polar, just like water, because your water is polar, but water and water alone is a hydrogen force. Okay, so water is a polar, and non-polar, let's say um, oil. Oil is non-polar substance. But anyway, the molecule of oil is so big, so I'll just put the chemical formula, not the structural one, or somewhat the general chemical formula, which is somewhat, let's say, that is a C18 H23. You just have to times 2, 1836. So it's really a big molecule. 37, I think, and then you have 37 COOH. I'm not sure with that name, but usually uh, oils come what has big atomic weight. So C18, C20, C21. Okay, so these are non-polar substances. As you can see, they do not dissolve in water. So gasoline also are non-polar substances. If you have a polar molecule near a nonpolar molecule, just like water and oil, those in between them, as you can see that when you have a glass of water and oil, where oil is at the top, the in between where the layers of water and oil meets, there's a force there. We call it a dipole-induced dipole. Dipole wins. Water wins. Okay? So dipole inducing its force on the on the non-polar substances. So that's why it is called dipole-induced dipole. But if it's a dipole with an ion, of course the ion wins. So that's why it is called ion-induced dipole. Okay? You can see the difference. You only have to look at it at the polarity and the ionic substances. So the last one is a hydrogen force. Actually, hydrogen force again is a dipole-dipole force, but the condition of it is it must have a electronegative substance, particularly oxygen, chlorine, and fluorine. I think these are the only three. Electronegative substance, as long as it has these three, and as you can see, it has the biggest electronegativity from the one that I've shown you. As long as it has that three, and you have a hydrogen, there is a special bond between that hydrogen part and these electronegative substances. Of course, substances which has this, for example, your water. Your water, H2O, of course, has hydrogen and oxygen. You can see you have hydrogen and you have oxygen. So oxygen is included in the list. as long as you have that three. Oxygen, so near a hydrogen, oxygen, hydrogen, there's a special bond between them. This is also dipole-dipole, but it is stronger generally with the dipole-dipole forces. That's why it is already on another level. So we call this force a hydrogen force, a hydrogen bond, sorry. A hydrogen bond. Sample, you have an NH2 near with an H2O. So you have water, water, and then you have hydrogen. So not the hydrogen here, but the nitrogen in your NH2. So you have your NH2, and still you have, I think, another two unpaired. So NH2, NH3, we can put another hydrogen here, of course, to make it a bit stable. NH2 is not really that stable, but NH3 is. We call it ammonia. So hydrogen with respect to oxygen here. So you can see you have hydrogen, and you have one of those elements or atoms as the most electronegative. Again, the condition is electronegative atoms, oxygen, chlorine, fluorine, and then you have hydrogen. There's a particular bond here. We call it hydrogen bond. Okay? So actually, they are also non-polar, but they are somewhat stronger than the common dipole-dipole force. So that's what makes them a hydrogen, not hydrogen force, but hydrogen bond. So usually it is called a hydrogen bond, not hydrogen force, because it would be misleading if you'll be talking about a force from hydrogen. So it's called a hydrogen bond. This is the reason why water is so unique. That's why it has to have its own criteria, because water is so unique with respect to other substances, and we know that water is one of our best solvent and one of um, what Earth is made of. Of course, we are as a human as we are I think 90% water by volume, meaning a lot of water in our cells. Even our blood, you have cells in it, but inside the cell there's also water. Outside the cell there's also water. Okay? So blood alone has water in it. That's why we always drink water. Okay, we sweat from the excretion of our waste from our cells. It excretes its waste through our ihi. Okay? So you have water, and um water is so unique that it has to have its own bonding, hydrogen bond, with respect to to polar substances. So those are the um, five. So as much as possible, we can identify. So prerequisite of this, you can already draw the Lewis structure of some molecules. So you can already imagine the symmetry, polarity. Then another one is, of course, you can imagine the electronegativity and all of those things. And that's why we have this LO. We can already identify if we are given atoms two atoms or molecules, or atoms and molecules, let's say an ion and we can already figure out what is the intermolecular force between them. Some books call it secondary bonds. Okay? That's why they are also termed bonds. Because the primary bonds are the atomic bonds. The bonds between what makes them a molecule and what makes them an ions. Okay? So thank you guys for listening. So that is the LO. You can name what are the, of course you only have to, you need that, but there are only five. You can memorize them. Come on, you can memorize them. But anyway, if you cannot, during quizzes, you can just list them as five forces as long as you don't have any examples. Okay, I can allow that during quizzes. Thank you guys for listening.